All right, workshop groups. Let me try another solution to your practice exam as you guys are practicing along here. Let me try number 12. I think this is, I guess, my fourth one here. It says an object of mass 1 kilogram moves in the positive direction along the x-axis. Okay. It is subject to a force given by this function. Where b is some constant number. And between the times of 1.89 and 3.35, the object's change of speed is. Now this sounds like a work energy process one. We could do it with kinematics. Oh, yeah. I'm sorry. In fact, let me just pause for a moment. My general argument here is if you know force as it relates to distance, it's a work energy problem. If you know force as related to time, then it's a dynamics problem where we have acceleration and whatnot. And we have it with time. And for some reason, I said that this was a work energy problem. And no, that would be probably a mistake to go down that road. So, but this will give me a chance to talk about, and one of the challenges of taking a final exam is you've done so many different stuff throughout the semester. One of the things you got to ask yourself at the very beginning is, what type of problem is this? Is it a kinematics problem? Is it a dynamics problem? Is it an energy or work energy problem? Is it a momentum problem? Is it a rotational problem? Is it a statics problem? And so those are the kind of topics, big picture topics that you guys have done. But this would definitely be a kinematics / dynamics because I got force here, and so I should integrate that here. So it asks for what is the object's change in speed. So an object, and it moves in the positive x direction. Okay, so I'm going to do hopefully the obvious, but maybe not. Acceleration is the derivative of velocity with time. But if you rearrange this equation and move the dt over to here, acceleration dt is equal to dv, meaning an acceleration for a very short amount of time is equal to the change in velocity. And so then if we apply our calculus, that means we're going to add up a bunch of change in velocities. And in our case, let's go from the initial velocity to the final velocity. So that's going to be my integral, which is actually perfect. I'll do that one first because the integral of dv is just v evaluated from some initial to some final. And that just means final speed minus initial speed, which is your change in speed. So that is what we are being asked for. What is the change in speed? So on the other side of the equation, where I have an acceleration and dt, I'll just put delta v, is then I can apply my dynamics here. I'd say at this point I'm doing the kinematics, but this would be force divided by mass, dt, is equal to the change in velocity. And so as the force said, it was bt, and then I can divide it by m, and I can integrate it from dt, and there would be some initial time to some final time. And I will put those numbers in just a second, but let's see. All integration, or every time you do an integration, you should pause and say, okay, what constants do I have? And so then I just have an integration of t dt. And again, from some initial to some final. And so this becomes a b over m, and the integral of t becomes t squared over 2. And then my limits, let me go ahead and put in the numbers now. They say the initial time is 1.89, and the final time is 3.35. Okay. So now I can actually, I think, do a calculation by putting in my numbers. Here's B, 4.06. So 4.06 goes in for B. And if I divide by M, which is just 1, so there's the B over M. In fact, let me just put the 1/2 there. And so then I would have my times squared, 3.35 squared minus 1.89 squared. All right, so now I can get my calculator. So 3.35 squared minus 1.89 squared would be that number. I'll go times 1/2 times a 4.06, and I'll divide by 1 because it's in the formula, but that's wasted time. Anyways, I get a change of speed of 15.5. And hopefully, sure enough, there it is right there. Okay. By the way, it might be very tempting on this problem to do some of those kinematic equations we learned, like distance x equals to initial position plus initial velocity times t plus 1/2 at squared. Another one was v in the x direction was the initial speed in the x direction plus acceleration t. And then let's not forget the final speed squared is equal to the initial squared plus 2 times the acceleration times the distance traveled. Then, and let me not write out the other 2. There's a nice common 5 of them. These are probably the most popular ones. But that being said, those only apply to constant acceleration, which means you have to have constant force, and we don't have that here. So notice I did not try to do the problem using any of these constant forces or constant acceleration ones, and that's easy to be careless and just kind of plug blindly into these, but you need to know where they came from. They came from doing an integral, and we would have derived them if we had constant acceleration here. All right, well, I'll call that one quits. Hope that helps.